In the previous session, we discussed about a proof technique which was direct proof technique. But remember, in most of the scenarios, this direct proof technique is very difficult to implement, because often, even if we do the backward calculation, it is not possible for us to find what is followed from which is followed from what and what follows which. So that is actually always not implementable. So in these scenarios, to deal with the system, but one of the most often used proof technique that I'm going to discuss right now. Okay, and that proof technique we often use, and you have also used at some point of your lifetime till date. Okay, so that particular proof technique, you can say it as technique 2. Previous one is technique 1. This is called, its name goes like this. It is called contrapositive proofs. Contrapositive proofs. So let us try to know what is this. Now we have two statements, capital P and capital Q. And as before, we want to show that P implies Q. Suppose we are unable to find the direct proof in this particular case. Okay, so what we do, we, instead of writing a direct proof, we try to show that not Q implies not P. We already know that truth table of P implies Q and not Q implies not P, they are same. Okay, so you can now quickly check whether you are comfortable with this or not. If you have not done it, you can quickly find the quick truth table to test it. But since these two truth tables are same, so since I am not able to directly prove that Q is being followed from P, I'm going to try whether not P is being followed from not Q or not. So such type of technique is called contrapositive techniques, and it is often used in mathematical community. Let me show you one theorem which can be a very well-known theorem, and probably you do not know it as a theorem. It is, you know it as a result, which way I'm going to try by applying this contrapositive technique. So what is that? If phi is a null set and capital A is any arbitrary set, then phi is a subset of capital A. Okay, so in this particular proof, or it is also written in short, null set is a subset of every set. So null set always can find a place in the power set of a given set. Okay, so how can we prove it? Actually, when we try to prove prove that capital A is a subset of capital B, what we actually do, this is the kind of thing which you can think of as a rough work. So when capital A and capital B, we what we do, what logic we apply, we write that, yeah, okay, let us assume that an element X is belonging to capital A, and after some argument, I'm going to show that X belongs to capital B, and by definition, capital A is a subset of capital B, because every element of capital A is a subset of capital B, is an element of capital B, and then we say that A is a subset of capital B. And since X is arbitrary, so it is true for all X. We write it like this. But here we cannot do so. We cannot say that let X belonging to phi. We cannot do so because phi is a null set by definition. Okay, so direct proof will not be applicable. So therefore, we try to do it by contrapositive argument. So let us try to write the things properly first of all. So your P is, you can say that, okay, before you write P, you can say that let capital A be any set. Okay, this is your context. This is the context that you have built. That means we have known that you are actually talking about sets, any set. Your capital P is, so I'm writing here, this is a context. Okay. Now capital P is phi is a null set. Okay. And capital Q is phi is a subset of any set. Phi is a subset of any set. Phi of a subset of capital A. A is arbitrary. Now try to follow, try to see what I'm going to write. If possible, let not Q is true. Okay, if possible, let not Q is true. That is, you know, not Q means not of phi subset of A is true. Okay, this implies not of phi subset of A. That means phi is not a subset of A is true. This implies there exists an element in phi which is not a member of the set A. Because by definition, capital A is a subset of B, it means that every member of capital X is a member of capital B. I'm writing over here, A subset of B. This implies, or double implication, every member of capital A is a member of capital B. So if you try to negate this, what I'm writing? Okay, I'm writing every member of capital A, every member of capital A is a member of capital B. So I can write it in this manner. For all X, X belongs to A implies X belongs to B. Now you already know from our previous discussion that if I put a negation over here, what does it mean? It means there exists X such that This is true, isn't it? And you know what happens next? I'm not going to write it over here. I'm just trying to remind you about the discussion of my last class with the current discussion. So that's why I'm writing that there exists an element in phi which is not a member of the set A. You can ask me whether you can apply these symbols over here. Answer is yes, you can write the things in symbol. But since you are learning, you are novice in these things, so I'm trying to use less symbol over, because otherwise you will not be able to follow my suit. But you see, when I say that there exists an element in phi which is not a member of the set A, we see that let us call this argument. Let us call this argument as say R. We see that R is an invalid argument as phi by definition contains no element. So somewhere at some place we have done something wrong. That's why we have come to this absurdity. I will call it as absurdity. Absurdity. This R, I'm calling it as absurdity. I have come to this absurdity because of something which is actually been stated wrongly. And what is that? What is that? This thing. When I'm saying that not Q is true, then that is actually giving you this kind of absurdity. This absurdity, however, further implies that if I say that there exists an element phi which is not a member of the set A, if I stick to this absurdity, it implies that phi is not a null set. And this implies not P. But the entire thing, starting from this part to that part, is absurd because it actually contradicts. This actually contradicts my assumption that phi is a null set, which contradicts the assumption that phi is a null set. So P implies Q. And this is your quod erat demonstrandum. So that proof technique is actually called a contrapositive proof technique. I'm going to show you this, since this proof technique is new to you, I'm going to show you another result, another theorem, another proof of the theorem, which directly comes from the real analysis chapter. This proof theorem is very important, and I'm going to show this by the technique of contrapositive argument. Let A greater than or equal to 0 be a real number if for every epsilon greater than 0 we have 0 less than or equal to A less than epsilon, then A is equal to 0. You can ask me that we didn't know this result. We have never applied this result. Why are you saying that this result is important? It's a significant result. We have never come across this result. You are a mathematics teacher. That means you know the result. That doesn't mean that we know the result. Yeah, yes, you are right. You don't know this as a result, but you have used it. When your teacher taught you limits of a sequence or limit of a function, you often wrote the thing like this: fx minus fa less than epsilon greater than or equal to 0. Okay, and after some argument, you wrote that limit x tends to a, therefore fx is equal to fa. And actually, you wrote that in this particular case, you wrote that somehow you wrote this thing that fx becomes exactly equal to fa. How does it so? Try to look at this theorem. Mod of fx minus fa is 0, non-negative, and is less than epsilon. Epsilon is arbitrary. That implies a equal to 0. So this implies fx equal to fa. And therefore, you wrote that, okay, fx equal to fa when limit x tends to a. So actually, we applied it many a times to prove even this result. If I take this sequence of numbers, we can find out the limit of the sequence, limit n tending to infinity, 1 by n minus 0 is equal to 1 by limit n tending to infinity 1 by n is equal to 0. And for this also, we actually try to show that 1 by n mod of 1 by n minus 0 is non-negative and is less than epsilon. We kind of build this argument in real analysis. So actually, the thing has not been known to you as a result, but we have applied we have seen its implications in different chapters. We are going to write this. We are going to prove this particular result with the help of contrapositive argument. Okay. Now, we want to show that a equal to 0. This is true. And the premise is, this context is that we are talking about real numbers. So this is my context. My context is the set of real number. For every epsilon greater than 0, we have this, that is our capital P, and this is my capital Q. Just to save time, I'm writing in this particular manner, although you know that you cannot underline things and put alphabets, doesn't have any meaning. So then we can follow in the following manner. If possible, let a equal to 0 is false. That is, not Q is true. Okay. Then since a greater than or equal to 0, we must have a greater than 0. Why? Because you have told that a equal to 0 is not possible. So there is only one possibility, that a must be greater than 0. Now, here also a kind of trick will be applied. You have to remember this part. Let us choose my epsilon to be kind of a specific, having a kind of specific value, which is epsilon naught and which is a by 2. We can do so because epsilon is arbitrary number. We can put any number, it is our choice. Then as a greater than 0, this implies a by 2 greater than 0. So epsilon greater than 0 is being verified over here. Okay. And it is obvious that if A is a real number, A by 2 is less than A. That means your epsilon naught is less than A. So the hypothesis zero less than or equal to A less than epsilon for all epsilon, is false. That is, not P is true. So it is an absurdity, and therefore P implies Q, because not Q was implying not P, and that is not true, because P is your hypothesis, and therefore this absurdity comes directly from your assumption that not Q is true, and therefore it is wrong, and therefore P implies Q. By similar argument, you can also prove, I am leaving it for you to prove that root 2 is an irrational number. Okay, you can also prove, do this example, prove or disprove the statement all birds can fly. Okay, and so on. The last top technique which I'm going to discuss in my today's class, let us call it proof technique 3, goes like this. Its name is proof by contradiction. Proof by contradiction. So what does it mean? It means that this method of proof employs the fact that if capital C is a contradiction, capital C is a contradiction, that is a statement that is always false, such as something like, say, 1 equal to 0, this kind of statement, you know, that is always false, then the two statements P and not Q implies C and P implies Q are logically equivalent. Thus, we establish P implies Q by showing that the statement P and not Q implies a contradiction. Now you can see very well that this particular technique, that proof by contradiction, is not a contrapositive argument kind of thing. It is something different. So this is the thing, this is the trick which we apply in this particular kind of technique. It is a kind of formalism that is applied in this kind of proof technique. Okay. We want to prove that P implies Q. We want to prove that this conclusion Q is coming out of this hypothesis. We cannot do so directly. So we want to build that if we consider this hypothesis and the negation of the conclusion together, okay, then together they imply something which we can call contradiction. By contradiction, we may mean a kind of thing which is always false, and it's quite obvious that 1 equal to 0 is always false statement. So such kind of thing will be obtained. And since these two arguments are logically equivalent, so if I can show this, then I can imply that it is true. So let me show you an example by mentioning a theorem. Let's do it in the next page. Okay. Theorem goes like this. Let A greater than 0 be a real number if A greater than 0, then 1 by A is greater than 0. Okay, so let us try to use the proof technique 3 over here. So let us write. Let's go back to our previous page, that we need to show that P and not Q together imply a contradiction. Fine. So here you see that this is my P, A greater than 0, and that is my Q. So let's see what is going to happen over here. Okay. So we suppose that the statement A greater than 0 is true. That is, capital P is true. Fine. And the statement Q 1 by A greater than 0 is false. That is, not Q is true. Okay. Therefore, if 1 by A greater than 0 is false, then 1 by A must be less than or equal to 0. This is the only possibility, because this is, again, I'm saying that this is the context. The context here is the set of real numbers. So you try to visualize the thing from the perspective of real numbers. Okay. So we have got this, but since A greater than 0 is true, it follows from the order properties. It follows from the order properties of the set of real numbers that a into 1 by a less than or equal to 0. Since a into 1 by a is equal to 1, therefore we are actually getting a contradiction which is 1 less than or equal to 0, because we know that it cannot be true, and therefore P and not Q is leading to the contradiction that 1 less than or equal to 0, which is a contradiction that we call as contradiction. Therefore P implies Q. That is, a greater than 0 implies 1 by a greater than 0, and which proves my desired result. The only requirement to this particular problem, is this: order properties. Now suppose someone doesn't know about order property, then he cannot proceed. Someone who doesn't know about order property, he cannot proceed. And I have seen that if I talk about the children, they don't know about real numbers, but they know about 1, 2, 3, 4 up to going in this manner, and very large and very large and very, very large. They do not have the notion of infinity. Okay, now suppose the child is not actually know about 0. Okay, because 0 is not a natural number, it is not a counting number. Now if you say and suppose the child knows about greater than symbol and less than symbol, so what she knows about natural numbers, she knows about greater than, less than, equal to, but she doesn't know about 0. Now if you write that 1 is less than 0 or 1 is greater than 0 and show that thing to the child, she will not understand, because the notion of 0 is not clear to her. Say, so to understand this thing that 1 is greater than 0, 1 is less than 0, she has to know about that 0 is a number and it comes before 1. Similar to that, when you are dealing with this proof, the only requirement that you need is to know the order properties. The order properties where I have applied that if a greater than 0 and 1 by a is less than 0, then their product is less than 0. If one real number is positive, another real number is negative, the product is negative. If one real number is 0, another is 0, their product is 0. These order properties you have to know very well. And if you do not know these order properties, so you will not be able to proceed to reach to the given requirement. So that is the thing which is actually needed over here. Similar manner, in a similar way, I am giving you another example. Just you can take it as a homework that show that there are infinitely many prime numbers. There are infinitely many prime numbers. Now, this proof which I'm writing over here, if you find any difficulty to do this particular proof, you can ask me, I'll give you the solution. But since today there is no much time left, so I will not be able to complete this particular proof, but at least I can give a reference in which you can find this proof. The reference is a book. It is the book Euclid's Elements. book 19, proposition 20. Okay, I'm giving this particular example from an exercise. So that's why in the exercise, these things, you don't think that I can memorize the entire elements. Okay, I'm giving it from the exercise. You have the library Genesis. You can download Euclid's elements and you can see the proof written over there. Or the shortest possible technique is to go and check it in Google, or you can maybe you can find it any other book you have on real analysis or whatever of this kind. But this is a very elementary proof, and this proof can be done using the proof technique, which is called proof by contradiction, that I can tell you about. This is a hint. Before I end my today's session, I must tell you about one thing, that if you ask me, how do we know that a particular mathematical statement is given and which particular technique we are supposed to follow over there, then answer to this question is not known to me. I cannot say that a particular theorem, if a particular argument is given and you want to build some other argument from it with some valid statements in between, then which particular technique we are going to apply. There is no hard and fast rule for doing this. That in this type of problem, you try to think of proof technique 1. In this type of problem, you try to think of proof technique 2, that is contrapositive argument. In that type of thing, you try to think of proof technique 3, method of contradiction. There is no hard and fast rule. When we are actually faced with a mathematical argument and we want to prove something, then actually we test everything. We test everything and we say that, yeah, okay, then I think here in this particular case, this technique is legible. That in that case, that technique is legible. And I have already showed you that when I talk about phi is a null set, which is a subset of any set, direct proof technique is not legible over here. Okay, and it is also true that in some problems are there where you can apply all the techniques and all the techniques are feasible, and by any technique you can reach to your ultimate solution. That can also happen, but beforehand that is not known to us. It is only a matter of time that you actually are able to find that which is suited the best for your given mathematical argument. So with this discussion, I know that this discussion remains incomplete if you do not try the things at home. If you don't study at home, everything remains incomplete. So I can at least say that all the topics of unit 3 of your syllabus has been touched upon. Rest is up to you to take the problems and do the sums. I'm going to upload very soon my yesterday's video and today's video. There will be in total 4 videos, because 4 sessions were taken. And before that, I'm going to upload one very 117-page book on mathematical logic. It is a very good book. You can study all the topics of unit 3 from that particular book. That will be your note. I have not prepared any note by myself. So I'm going to upload that in Google Classroom tonight. So hope you have enjoyed. See you next week. Till then, bye.